Hello and welcome to From Data to Decisions. I'm Chris Mack, your instructor for this class. And this lecture, Lecture 41, we're going to do something a little bit different to review what we've talked about so far regarding regression. In particular, we're going to review regression diagnostics and remediation. So let's talk about the assumptions in an ordinary least squares regression. We've seen this slide so many times, it should be very familiar to you. There are 6 assumptions, one of which is always going to be true if we have a model with an intercept. So number 2, mean value of all the residuals equal to 0 is not something we're going to worry about. The other 5 assumptions are things that can and do go wrong in many regressions. That is, they're not always good assumptions to make. We need to check them, and if it turns out that the assumption is not a good one, we need to do something about it. First, assume the model is perfect, so that residuals only contain random components. Then we assume all the residuals are independent of each other. We assume that they're homoscedastic, that is, they all have the same variance and same PDF, probability density function. We assume that the residuals are normally distributed, and we assume that each of the predictor variables are known exactly. And we've talked about how to test for each of these and what to do about them past 40 lectures. Why do we worry so much about ordinary least squares regression? Well, it's a very simple reason. If the assumptions of OLS hold, then OLS provides the best linear unbiased estimates of the parameters of our model. By best, we mean the lowest variance. If they're unbiased, that means if I repeat the experiment over and over and over again, I will get, on average, the correct value. It's an unbiased estimate of the true value. And best means the lowest variance. That means we're going to have the tightest confidence intervals about those parameters. These are both very, very good things that we like about OLS, which is why we always want to use it. But it's only true if the assumptions are valid. When they're not, we have to do something about it. Well, one thing we could do is use other regression techniques like robust regression or generalized regression, but they're not as efficient. They produce larger confidence intervals. So we will only go to those techniques when we have to, and we're going to talk about those techniques later in the semester. We haven't gotten to them yet. So far, we've only talked about versions of ordinary least squares regression. So the overall regression process is broken up into 2 steps. And the second step has a lot of pieces to it that we'll go through. First step is to pick and run the regression, create our best estimate of the model parameters. Generally, we're going to try to do ordinary least squares regression first. That's our goal because it's the blue, the best linear unbiased estimates. But if not, we can do some other things. We can do a weighted regression. We can do a total regression, one of the various options, which are kind of versions of OLS that are appropriate in certain circumstances. If we can't do OLS, then we might have to do generalized linear regression or robust regression. And sometimes we might have to do nonlinear regression. We're going to discuss all of these things later in the semester, but we haven't talked about them yet, so I'm not going to talk about them today. Then the second step is to plot and study the residuals. This is the diagnostics and remediation phase of regression. So if we're going to use OLS, we got to check to make sure that all those assumptions are valid. So what does studying the residuals mean? Well, it starts by plotting the residuals. And the kind of residual that we want to plot, mostly what we test is the externally studentized residuals. We plot them versus the regressors, and we plot them versus the predicted y values. Then we look for outliers and influential data points. We check for normality. We check for homoscedascticity. We check for model error. And we check for residual independence. We don't always do this in this exact order, but outliers and influential data points should be the first thing we do. And then we'll often iterate, right? We might see some model error very early on and deal with that before we go off and deal with else. We might have to deal with outliers before we check normality, but if we check normality and find that it's not a normal distribution, that affects the way we check for outliers, right? So this is probably an iterative approach more often than not, rather than a sequence. You do one, then you do the other. Nonetheless, I'm going to talk about them as if we're doing one after the other here. So after we've plotted, we're going to look for outliers in influential data. We do that by calculating the leverage, the internally studentized residuals that come from that leverage, externally studentized residuals that come from the internally studentized residuals. Then we'll calculate the Cook's distance and the DF fits for each data point. This gives us a sense of whether any particular data point is overly influential in its ability to affect the fits. Likewise, we can look at the DF betas for each model coefficient to find out if any particular data point is overly influential in its influence on the parameters of the model. All of these are useful things to look at. I find, especially as a first look, the most useful thing to do is to construct a Williams graph. We plot on the Williams graph magnitude of the ESR versus the leverage. We can put a line, horizontal line corresponding to Grubb's critical t-value, and a vertical line corresponding to twice the average leverage, and look for leverage, high leverage points, potential outliers, and most importantly, highly influential outliers. If we need to, we might perform the Grubb's test on the ESR of a single outlier. That's easy to do, or more complicated is when we have more than one potential outlier. And if we find some influential outliers, we have to decide what to do with them, and that's not always a trivial thing to do, and we've discussed some of the options in those lectures. After we've performed our tests and we've dealt with all of our outliers, we're then going to check for normality. Now here's where the iteration might come in, because if we find out that after dealing with the outliers, the resulting distribution is non-normal, that might influence our previous decisions, whether or not we throughout dealt with an outlier. Because our outlier testing, like the Grubb's test, assumes a normal distribution, right? So we might have to iterate here. But let's start by just checking for normality. We'll plot the ESR as a histogram and ask, is it unimodal? That's the only thing we're going to really get out of our histogram is if we see two modes or one. Normally we'll see just unimodal data, so that'll be fine. Then we'll do the real work, which is to create a normal probability plot or a QQ plot. From that, we can see if it looks like we have light tails or heavy tails or skewed data. If it's a strong departure from normality, we may look for a non-normal PDF that we can see if it matches. So we might pick some other distribution, see if we can find a different distribution that better matches the way our residuals are behaving. If it only looks a little bit non-normal, we can't really tell for sure, we might do some tests like moment testing. Test for skewness. If we pass the skewness test, we'll test for kurtosis. If we pass those tests, we might check for heteroscedasticity. Now, normally we're not going to do a heteroscedasticity test unless there's something about the plots of the residuals that make us think that we should do that kind of a test. All right, if we can't really see any heteroscedastic behavior, then we really don't need to worry about it too much. It has to be fairly strong variance, change in the variance, one portion of the data to another portion of the data, before we worry about it too much. So if we notice it in the plots, then we'll go ahead and do either a Bartlett or a Brown-Forsyth test for heteroscedasticity. We'll check for model error. We might do this earlier in the process, depending, because we'll start with the residual plot. And the residual plot, it may be obvious very clearly that we have model error and we need to do a better job of finding the right model. But it's not always obvious from the residual plot, in which case we might come back after we've established that we really do have a normal distribution of residuals. We'll do an overall F-test. Now, the overall F-test, in most cases, it's going to pass. I mean, if you have any kind of a reasonable model, if you have any kind of a systematic trend that your model is capturing, you will pass the F-test. So it's only in kind of extreme cases of I can do a fit. I'm not really sure if I'm fitting the noise or a real trend. Will you worry about this F-test? In a lot of cases, it's obvious that you're going to have a large F value and a small P value. Nonetheless, these F-tests are almost universally done automatically every time you do a linear regression. You might also do a chi-square test. This is something you do if we have some Y measurement uncertainty, or if you're doing a total regression with Y measurement uncertainty and X measurement uncertainty. If we have these independent estimates, we can look at the model and ask, is all of the variability in the Y values explained by the model plus measurement error? If not, then we know we either have a wrong estimate for the Y measurement error or we don't have the right model. We don't have the perfect model anyways. It may be good enough, but we don't have a perfect model. When we do multiple regression, we're going to have to check for something else, which is correlated parameters. But that's a subject we're going to talk about actually next, right? This is the first part of the class where we're only doing bivariate regressions, one predictor variable. But later on, we're going to have to worry about some other things. So keep that in mind for the future. Next, we're going to check for the independence of the residuals. We'll do that with a lag plot. We'll begin by plotting the lag plot, the residuals versus the residuals lag 1. If we see some correlation, we can calculate the correlation coefficient. And then we can ask, is this correlation significant, by running the Durbin-Watson test. And that will help to let us know whether or not the correlation we see is just due to randomness or, in fact, it's really there. If we detect correlation, the next thing we'll do is create an autocorrelation function plot, which is simply the correlation coefficient versus the lag k, and try to see what kind of behavior exhibits. If it exhibits an exponential decay in R versus lag k, then you might be able to do something with an autoregressive lag 1 model, an AR1 model. If needed, we might transform the data based on the AR1 model, form the OLS, and transform the data back, or the model back. Or we might try to fix our experiment or otherwise improve our process of collecting the data to eliminate the correlation between the residuals. And finally, after we've done all of this, we have a model, we have a result. Present those results. When you present regression results, you always need to talk about your confidence in those results. You need to talk about which regression approach you used and why you used it. If you used OLS, can you justify all of these assumptions? Right? You need to explain why you believe the assumptions of OLS are valid. If there are any regression assumptions that were not met and not fully remediated, you need to talk about what those are so that people can evaluate to trust the results because of that. And finally, every time you present a model result, you need to present confidence intervals or standard errors for each of the model parameters. Sometimes you might be only interested in one of the parameters, the slope, let's say, and so maybe you'll only present the confidence intervals for the slope, not the intercept, but that depends on the circumstances. If you're going to make predictions using the model, you also need to add confidence intervals around your predictions. Users, people who read your paper or see your results, they're not going to be able to figure out what these confidence intervals are unless you give them all the data and they can reproduce these results yourself. So it's very important that you supply standard errors of the confidence intervals for each of these items. There are two uses, two goals in doing this modeling. The two major reasons why we do regression modeling is to create a model with predictive ability or to create a model with interpretive ability. So in predictive ability, our goal is to make predictions and when we make predictions, we need to put confidence intervals around those predictions. Sometimes our goal is to use the model to interpret the world, to say, oh, look, this behavior really is linear, or this behavior really is logarithmic, or whatever it might be. This parameter really does have no influence on the results. Again, interpretive ability, which usually means interpreting the meaning of the form of the model and the coefficients on those models, requires us to put confidence intervals around the model parameters. You have not done a regression unless the regression includes confidence intervals around your results. Well, that's a very brief summary of what we've done for the last, what's it been now, 6 weeks, 8 weeks almost? I guess closer to 6 weeks, 40 lectures. This is lecture 41. We still have plenty to go. We have to talk about other kinds of regression, and in particular, multiple regression, which will lead us then to the major topic of the second half of the course, which is model building. What does it take, if you're starting from scratch, to build a model that you trust, that you like? Till then.